Okay, so we're going to start off with problem 6.24. In this problem, we're asked to find all of the forces and the numbers above HJ. So here, let me draw in where HJ was. HJ is right here. So that just means we take a section through the members that are above HJ. So let me redraw that section over here. And we're obviously going to have to replace the forces of the members that we cut through with forces. So we have just this part now, and then we're going to have forces acting here, here, and here. So I'll call this force CH. This is EJ, and then we have EH. And EH is a 3, 4, 5 triangle angle. So just to make that easier. Okay, and then we have our two forces acting down here of 1.2 kilonewtons on each side. So this is our free body diagram of that entire section. So then we're going to do some of the forces. So sum of the forces in X is equal to 0, gives us, well, the only force there is the negative 4/5 EH. So that tells us EH is equal to 0. If we do some of the forces in the Y, yes, negative 1.2 minus CH minus EJ minus 1.2, and so we need to do some of the moments to solve for the last force there, or to solve for the last two forces. So the point we want to take the moment about, again, it can be at either point C or point E. Either one will give you the other force, but I'll just do it about point E. So it's point E. To end up with 1.2, which is 3.8 meters away, plus the force CH was 1.6 meters away. So CH. And then we're going to have a minus the 1.2 times 2.21. Again, this is just using a right-hand rule. It's pointing downward, so if you curl your hand in that direction, your thumb should be pointing into the paper or into the board. Okay, so this gives us CH. So let me just calculate that. This gives us CH is equal to negative 1.1925 kilonewtons. I'm just going to leave it as all the decimals there, just because it's going to be used later in the problem, so we don't need to round it off there. So then that'll give us EJ. So let's see, EJ is the opposite of CH minus 2.4. So that's EJ is then negative 1.2075 kilonewtons. So now that we have our first three members here, we can move on to a method of joints to get the other members. So I'll start that on the next page. So again, it's probably best to start at either point C or point E. So I guess I'll just start Actually, it's probably best to start at point C since there are only 3 members coming off of that. Let's see. Actually, I'll start at let me just take a look at the problem again. Okay, we'll start at point A then. So we'll have force AB here, force AC here, and then a 1.2 kilonewtons acting downward here. So first thing we want to do is figure out what angles these 2 forces are at. So we know it's going across 2.21 and then up 0.6. So if we simplify that out, it actually gives us a bit of an odd triangle here. So we have, these are both going sort of like this, with this side length being 221, this is 60, and this is 229. So that'll just make our calculations a little bit easier. So if we do some of the forces in the x direction, we end up with 221 over 229 AB plus 221 over 229 AC is equal to 0. So this just tells us AB is equal to the opposite of AC, which we can then plug into our sum of the forces in the y to solve here. So we end up with 60 over 229 AB minus 60 over 229 AC minus 1.2 is equal to 0. So if we plug in, let's just plug it in the other way around. We'll plug in AC is the opposite of AB. So that'll give us 60 over 229 AB. And then we're just adding that again. So I'm just going to multiply this by 2. And then minus 1.2 is equal to 0. So now we can just solve directly for AB and figure out AC from there. Okay, so this gives us AB is equal to 2.29 kilonewtons, and that would obviously then tell us AC is negative 2.29 kilonewtons. Okay, so there's 2 more members, and that was pretty simple yet. So now we can start looking at other points. We need these 2 forces to continue solving the problem. We can do the same exact thing on the other side. And if you notice, this is a pretty symmetrical problem, other than there's diagonal bars in the middle that won't be symmetrical. But for the endpoints, so here we have DF and EF. This is just the flip of what we just did. So we can actually just say by symmetry that's going to be the same. So again, this DF is going to be equal to AB, which is 2.29, and then EF is, so this is an F, EF is equal to AC, which is negative 2.29. Okay, and I mean, if you think about it, it makes sense because we're basically saying that both of these forces are going to be pointing in the positive y direction because they're both trying to counter that 1.2 kilonewtons in the negative y direction. So it makes sense that the bottom part would be in compression, whereas the top member would be in tension. So that's another simple 2 more members. So we already have 7 members solved, and we only need, I believe, 5 more. So problem's going by pretty quickly here. So now we can just start looking at some of the other numbers here. So we have this one is point C. Okay. So let me just write these forces in here. So we have CE, CH, BC, and AC. And we just said that AC was negative 2.29. So let me just write that in here. Negative 2.29. I'm going to check back. I don't remember what we got for CH. CH was negative 1.1925. Okay. And these are both measured in kilonewtons. So keep that consistent throughout the problem. So now, if we would want to do a sum of the forces in the y. So sum of the forces in the y gives us, I'll start with some of the forces in the x just because it's going to be a bit simpler here. So some of the forces in the x will give us CE minus, and then let's check back what we said for that. So it's going to be 221 over 229. Times AC, which was negative 2.29, equal to 0. So CE, we can then solve for we just get negative 2.21. Okay. And so now, when we do some of the forces in the y, we're going to have components from 3 vectors here. So we have BC minus CH, which I'll just put in as negative 1.1925, and then we want plus this times C over 229, and then that's times AC, which is negative 2.29. And this is equal to 0. So now we can solve directly for BC here. So let's just plug that in. And we end up with BC is equal to negative 0.5925. more of our members. So now we just need to do a few more members to solve the entire problem. So next one that we'll look at is, let's see. Let's look at joint B. This had just a force here. This was DF. And we have BD and DE. Okay. And so we already said before, let's see, DF was 2.29 kilonewtons, so I'll just write that in here. Okay. And so this is a pretty simple one. We just need to break DF into its two components. So we got some of the forces in the X is equal to 221 over 229 DF minus BD is equal to 0. And since we know what DF is, we can just plug that in to get BD. Just want to make this clear. This is a 2 here. Sorry about that. So it's just 220. Just going to be 2.21. And then we do the same thing, sum of the forces in the Y. Now it should be pretty obvious what this is. So we have negative 60 over 229 times 2.29 minus, that was DE, is equal to 0. So this is just going to get us a negative 0.6 kilograms. Okay. So there is, sorry, this is for D. Let me just write this again. So there's 2 more members. So at this point, we have 4 members here, another 4, and then we have 3 here. So how many members did we want to solve for? Well, if we look at the original problem, we have the 3 that we cut through. We have 2 on each side, so that's 4 plus 3 is 7. And we have 5 in the box, in the topmost box there. There are 5 numbers. So in total, that's 12, and we've solved for 11. So the only one we have left to solve, sorry, I went too far. The only one we have left to solve is the diagonal one in the topmost box. So we can pick either point B or point E to solve that for, and it doesn't really matter which one we pick. It's just they're basically opposites of each other. Actually, point B has 1 less member attached to it, so I guess we can do it there. Okay, so I'll just write this up here for now. So we're looking at number B here, so we have BD, AB, BC, and DE. Okay, and we know most of these forces. I'll just plug these, or I'll write these values in here. So we know this is negative 0.5925. BE is 2.21, and we know AB as well. Let's see what that was. We solved AB was 2.29. Okay, so the only one we don't know here is BE. So the easiest way to solve for that is to do a sum of the forces in the y, since there are only two other numbers that are going in the y. So actually we can do it either way. Sum of the forces in the y, so give us negative 60 over 229 times AB, which was 2.29. Minus BC, which is negative 0.5925. Oh, also we need to figure out what angle BE is at. So this is actually just a 3, 4, 5 triangle. So I'll write that over here. This is BE. We have this side length's 4, this is 3, this is the 5. So if we're doing it in the y direction, then it's going to be negative 3 over 5, or minus 3 over 5 times BE. And that's it. So this is equal to 0. So now we can just plug in all our values into a calculator and solve it. And we get BE is equal to negative 5 times 10 to the negative 4. So it's pretty obvious this is just a very small force in the diagonal here. And that makes sense considering there were no horizontal forces placed on that section there. The only forces were vertical, so it makes sense that the diagonal portion there would have a very small force in it. So moving on to our next problem, this one's a lot simpler. Hopefully should be able to solve it pretty quickly here. So this one, they're just asking us, using the method of joints, determine the force in each member of the truss shown. And then we're stating whether the force in the number is in tension or compression. So first thing we want to do is take the free body diagram of the entire box here. So we have 1 kip, 4 kips here, and 1 here. And then we're going to have 1 reaction at the roller, so we'll call that dy. And then we'll have 2 reactions at the pin joint. Oh, sorry, we also have another force acting here of 2.4 kips. And we'll have Fy and Fx. And just by looking at the problem, you can tell that Fx is going to be 0. So may as well get that out of the way first. So sum of the forces in the x is equal to 0. It's equal to Fx. So that's pretty obvious there. Now if we do the sum of the forces in the y, when you have dy plus Fy minus 1, minus 4, minus 1, minus 2.4. So those are just all the other forces acting on it or acting down. Okay, so that's equal to 0. And so then we need a moment equation to get the last part. So we can take that about either point D or point F. I guess for now I'll just do it about point D. So we know, sorry, this is moment. Some of the moments about point D. The force acting at joint A is also going through joint D, so we don't need to worry about that. And then, let's see, we have the two forces in the middle that are acting downwards. So those are 12 feet away, and they're, we can just sum them here, so 4 plus 2.4. And then we need a right-hand rule to figure out whether that's creating a positive or negative moment. So if you look with the right-hand rule, it turns out it's negative. So those are the first ones. And then we can do basically the same thing here. So we'll figure out whether it's a positive or negative moment in a second here. So let's see. So then we have other ones that are 24 feet away. It's Fy minus 1. So Fy is going to create a positive moment, and minus 1 will be negative, so we can just put a plus here. So that's our moment equation. So that will tell us Fy, and then we can solve for dy based off of that. Let me just write this is equal to 0. Okay, so this gives us Fy is equal to 4.2, that was in kips. And then we can say based off of that, dy is going to be, let's see, 1 plus 4 plus 1 plus 2.4 minus Fy. So dy is just going to be the same. And that makes sense. All the forces are equidistant from both points, so it makes sense that both of them would provide the same amount of force. So now we can move on to doing our method of joints. So we want to start, let's see, where do we want to start? So if you look at point D, there are 3 members coming off of it, yet we only know 1 force. So we can't start there. Same thing with point F. This is again a symmetrical, so you can tell where you can take forces from. So knowing that, we know that at point A, there's only 1 force acting on it with 2 members coming off. So we can figure it out from there. Okay, so first point we want to take is point A, and also due to the symmetry of the problem, it's going to be this point C. So we have a 1 kip force acting down here. We have force AD, and then force AB. And just by looking at this, you can already tell some of the forces in the X is going to AB is 0, and then some of the forces in the Y will tell us AD, so it's negative AD minus 1 is equal to 0, so that's to say that AD is equal to negative 1. And we can say the same thing, so here's one, here's the other. We can say the same thing for point C. So I'll just put this wherever there's room. We can say that BC is then going to be 0, and C is going to be the minus 1. now we just observe. Okay, so there's two more of our numbers solved. So now that we know AD and CF, we can start looking at either point D or point F. And again, due to the symmetry of the problem, we know that it's going to be the same for both of them. So let me just get out. Oops. Having some problems here. Okay, I'm going to recalibrate this pen for a second. Okay. See if I can get it. Okay. So now we just want to look at either point D or point F. They'll both give us the same values here because the problem is symmetrical. So we'll just look at point D. So we have AD acting up. We'll have DY here. We have a BD force acting diagonally and a DE force acting to the right. So we know, let's just go back for a second, DY was, where did we put it? Oh, DY is 4.2 kips. And AD is -1. So first thing we want to do is sum the forces in the Y. That will give us BD there. So let's see, it's equal to AD plus DY plus, and then we need to figure out what angle this force BD is at. So let's see. Okay, so this is, it turns out this is just an 8, 15, 17 triangle. So we'll write that over here. So this is BD. This side is going to be the 15, this is 8, and this is 17. So now, to get our Y value there, we're going to multiply by 8 over 17 times BD, and then we're going to set that equal to 0. And just move this over. Okay, so now we can solve for BD. And let me just also say that BD is going to be equal to BF. So just plug that into a calculator. And we get negative 6.8. Kips. Okay. So now we can do some of the forces in the X to get DE. So we get DE plus, this time it's going to be 15 over 17 times what we just solved for BD. So that's times negative 6.8 is equal to 0. Let's just pull out the old calculator here. Okay, and so we just get DE, which is also equal to EF, is equal to 6 kips. So that was a really fast way of just getting 4 members there, all in a pretty short amount of time. So let's see. So now we have everything except for force BE, I believe. Let's see, we have 4 members here. We have 4 members here. And in total, there are how many? Yeah, in total there are 9, and we have 8 of them. So now we just want to look for the easiest point to solve for force BE. So that's going to be at point E, because there aren't any diagonal numbers there. So we have DE, EF, 2.4, and BE. And actually, we don't need anything fancy to solve here. It's pretty obvious. You do the sum of forces in the Y, we get BE minus 2.4 is equal to 0. So that just tells us BE is equal to 2.4 kips. So that's our last number there. Very easy. So let's just move on to the next problem then. So, I guess I didn't write the number here. This is just the next problem, 6.5. It's another truss problem where they're asking us to use method of joints to find the forces in the numbers. So as always, we just have to take free body diagram of the entire thing. Only going to have one reaction at the roller, which we'll call dy. We're going to have 2 reactions at the pin here. Call that ay and ax. And then we have 2 other forces here of 10.8 kilonewtons. Or sorry, 10.8 kips. So just looking at it, some of the forces in the x equal to 0 is equal to ax. That's pretty easy. So that's our first reaction. Some of the forces in the y is equal to ay plus dy minus, and that's going to be just 10.8 times 2, because there are 2 forces acting downward. So then we want to take some of the forces, or sorry, some of the moments. We can take that about point A, and we get a pretty simple equation here. So it's going to be 22.5 feet times it's dy minus 10.8. And we know that's positive just because of a right-hand rule. And then minus, let's see, we need to add the numbers here, so it's going to be 57.5 times 10.8. And again, this is negative just because of a right-hand rule. Okay, and so we have, this is equal to 0, so that'll give us dy. dy is 38.4, and this is measured in kips. And so we can plug that into some of the forces in the y direction to get AY. We just write this is equal to 0. Okay, so this gives us AY is equal to negative 16.8 kips. So there's all our reaction forces. It's just double checking, making sure this makes sense. So does it make sense that AY is acting downward? Well, yeah, it would, because it's having to counter those moments generated by the downward forces, the two 10.8 downward forces. So it makes sense that that's acting downward, whereas DY is acting upward. So now we can start doing our, well, here, actually first I'm going to try to figure out the angles that these two diagonal numbers are at. So let's see. Okay, so this is simply a 12, 35, 37 triangle. Okay, let's just redraw that here. Okay, and so the other one, let's see. The other one we end up with a 12, 45, 51. So this is 12, 45, or sorry, no, 24, 45. Sorry, let's try that again. 24, 45, 51. Okay, so that'll just make it easier for doing calculations later on. So we can take some of the forces at any point where there are only two numbers connected, so that's either point A or point C, and then we can get the other forces based off of what we got from there. So let's just get on the sheet here. Okay, so we'll start with point A then. So we have force acting in the Y, like this. So we have AY, which we said was negative 16.8. We have AB, and then we have AD. So first thing we want to do is sum the forces in the Y. So here was negative 16.8 minus AD, and we need to multiply that by whatever the angle was, so it's 24 over 51. So times 24 over 51, this is equal to 0. So I'll plug this in. End up with AD is equal to negative 35.7 kips. Now we can do some of the forces in X. So we have 45 over 51 AD plus AB. So this just gives us AB is equal to 31.5 kips. So there's our first two members. Unfortunately, this problem is not symmetric, so we can't make it make it a lot simpler like the other problems. So let's just move on to point C then. So point C, we have a negative 10.8 here. We have, let's see, it's BC and then C. So we want the sum of the forces in the Y is equal to negative 10.8 minus, oops, let's see, it's 12 over 37 is equal to 0. So let's just plug that in. End up with CD is equal to negative 33.3 kips. And we can use some of the forces in the X. Yeah, negative BC minus 35 over 37 CD is equal to 0. And we obviously just solve for CD, so we can plug that in to solve for BC. And we get BC is 31.5 kips. So that's 4 numbers solved. Now it's really simple to get the last one. So we're going to look at point B. We have 10.8 kips acting downward. I have AB and BC. And this is also a good way to check your work. If you notice, in our calculations, AB and BC are equal, and since these are the only horizontal forces here, that makes perfect sense. So that shows that we did the calculations correctly. And then we're just going to have BD. Simply, sum of the forces in the Y is negative BD minus 10.8 is equal to 0. So BD is equal to 10.8. Sorry, it's equal to negative 10.8. I just realized I was supposed to go through and say whether these are in tension or compression. So pretty much whenever it's negative, it's in compression. Since we're drawing everything in tension, a negative tension is a compression. If you drew everything in compression, it would be, if it were negative, it would be in tension. So another way of writing these would be 10.8 kips and just saying compression. That way, if someone's trying to draw this out, they know which direction the forces are acting. So pretty simple there. Finishing a little early, maybe I can go start another problem here. So we'll just move on to 6.6. Just have a big box here, split into 2 smaller ones, with diagonals here. And then we have a pin here and a roller here. Some forces acting here, both 900 newtons. And then we'll need to dimension this. It's 3 meters. So it's 2.25, 2.25. Just for simplicity, I'm going to draw what these diagonal members, what their angles are. So let's see. So this is, let's see. This is a 4-5 triangle, essentially. So let me just write that down. This is 3, this is 4, this is 5. So since the dimensions are equal for both boxes, we know that both of those are going to be the same. So that makes this problem a lot easier. Let's start off with our free body diagram of the entire box. We have 2 forces here. So this EY, EX. And then the roller just has one reaction force, Fy. We have the 900, 900. Okay. So let's do, if we do the sum of the forces in the y, which is EY plus Fy is equal to 0. Now that doesn't mean that they're equal to 0. We're going to need a moment equation to get that. Or to get those values. So some of the forces in the x, we have EX plus 900 times 2 is equal to 0. So EX is equal to negative 900 newtons. So now we need a moment equation to get the remaining forces, or the remaining reactions. So I'm going to take it about point E since there are 2 reactions there. So let's see. Negative 2.25 times 900 minus 4.5 times 900 plus 3 times Fy is equal to 0. So solving for Fy, Fy is 976.5, and that's going to give us EY is negative 976.5. These are both measured in newtons. So we have 3 reaction forces here. So we can start at any member that has a force acting at it and has 2 members attached to it. So the only one that actually fits that, I think, is point E. So let's just start there. And this is really simple, since all of the members, or all the forces are going to be in the same direction. So we have EX, EY, CE, and EF. And so our sum of the forces in the X is EF plus EX is equal to 0. Let's see, our EX was negative 900. So this just tells us EF is 900 newtons. Sum of the forces in the Y is equal to CE plus EY is equal to 0. Our EY value was negative 976.5. 976.5. Pretty obvious. So now we can move on to point F. So point F is a little trickier because we're going to have this 3, 4, 5 triangle here. So we said this was 976.5 acting up. EF was 900. So, and then let me just write down the other forces for CF and DF. And it's pretty obvious, you just do some of the forces, and the X is equal to negative 900 minus, let's see, it was, in the X direction is 4/5, so minus 4/5 CF is equal to 0. Let me just plug that in here. Okay, so that gives us CF is negative 1125. Okay. Some of the forces in the Y is equal to 76.5 plus DF plus 3/5 CF, which is negative 1125. Equal to 0. Just plug this in to a calculator. We get DF is negative 301.5 newton. So now we can continue moving out of the box here. Move over to point C. We have AC, CD, CF, which we know is negative 1125, and then CE, which is 976.5. Okay. So first thing we want to do is some of the forces in the X. This is CD. Let's see here. In the X, it's 4/5. So plus 4/5. Let me just check again. Plus 4/5 times CF, so it's negative 1125, is equal to 0. So that'll give us CD is 900. We can do with some of the forces in the Y. AC minus 976.5 minus 3/5 times negative 1125 is equal to 0. So give us AC AC is 301.5. So we already have 6 members solved for. And I just realized I made a mistake here. There's actually supposed to be a force acting in the x direction here of 900. So let's see, we would have to take that into account for our some of the forces in the x equation. So I think that actually is saying CD is 0. Let's see. Let me just plug this in. So this plus 900 is equal to 0. Is that right? Yeah. So if we got CD was 900 before, we'd be subtracting 900 from that. So that just tells us CD is 0 newtons. So yeah, that looks to be right. I guess I just made a little mistake there. So next, where do we want to move to? We can move to point A, since we just solved for AC. So let's do point A here. So we have AC. Make sure to put the outside force here. We have the 900. And we have AB. And then we have a diagonal force here. So we just solved for AC. We said that was 301.5. And then we have this diagonal force here, AD. Don't believe we solved for that yet. So let's see, what do we want to do first? Let's do some of the forces in the Y first, since there's only two forces acting in the Y. So this is going to give us negative 301.5 minus, was it 3/5 AD is equal to 0. So this gives us AD is equal to negative 502.5 newtons. Some of the forces in the X, we have to take more into account here. So we have 900 plus AB plus 4/5 AD, which we just solved for, was negative 50. What was it? 502.5? Right, this is 2. 502.5 is equal to 0. So we end up with AB equal to negative 498 newtons. So I believe we just need to look at point B now. And yeah, point B is really simple since there's just two numbers there. There's no forces, so we just have AB and BD. And so some of the forces in the Y is equal to 0 is equal to BD. So that's another one there. I think that's it. Let's check. Let's see, there are 10 members here. So let's see, we have 3 here plus 6 here. Which one haven't we solved for? So we have EF, CE, CF, DF, CD, AC, AD, AB, and BD. I think that's everything. I don't know why I'm getting an amount here. 1, 2. Okay, I guess it is 9. There's miscounting here. So that's the end of the problem. Again, if it's negative, then it's, since we drew it in tension. If it's negative, it's going to be compression. So this is compression. This is compression. And where did it go? And these two are both in compression. So that's it.